Hello and welcome to Anesthesia Tools. This time we shall discuss gas laws and its applications. Disclosure or disclaimer, an exhaustive discussion on this topic is beyond the scope of this lecture, and this is not a core physics in anesthesiology discussion, rather an attempt to discuss a few practical applications of gas laws in anesthesia, which is nice to know.
Now, let us say, you need to find out how much oxygen is available from a cylinder. You don't need to think out of the box. Here's how you take help of the gas laws to solve it.
Okay, suppose you want to know how much oxygen is available from a cylinder. How do you calculate? In the standard textbooks, it's given that an E cylinder with 900 has a capacity of 660. So let us see, using gas laws application, can we derive that? Boyle's law is one of the very commonly used gas laws, and it says that for a fixed mass of gas at constant temperature, the pressure P and the volume V are inversely proportional when temperature is kept constant. That means pressure into volume is a constant. P1 V1 equals P2 V2, where 1 and 2 denotes two different instances. Okay. So our routine service pressure at which oxygen cylinder is filled is, let's say, 2000 psig. So now we have a scenario of oxygen in E-type cylinder with a volume of 5 liters, that is V1, with a pressure of 2000 psig. So when it is released into an atmospheric pressure of 15 psig, that is P2, what is its volume? Now the calculation becomes more simpler. P1 into V1 equals P2 into V2. That means 2000 into 5 equals 15 into V2. Solving it, we get 666 liters. Hope it is clear. So if we use 3 liters of oxygen, the E-type full oxygen cylinder will last for 660 by 3, 220 minutes. Okay, a little over 2.5 hours. And last 5 liters of oxygen will remain in the cylinder and cannot be used because there won't be pressure difference in and out of the cylinder. So the practical application would be when we decide for patient transportation with oxygen supplementation with oxygen source cylinder, we should check the cylinder pressure and see how much of oxygen will be available from that remaining oxygen cylinder. Again, while troubleshooting pipeline supply during an anesthesia, anesthesia workstation demands half filled, that is 1000 psig pressure oxygen cylinder as backup, which should mathematically should give you 330 liters of oxygen backup. Remember, most of the anesthesia workstations, the ventilator drive gas will consume oxygen equivalent to the minute ventilation of the patient also. So if you want to buy more time in troubleshooting, switch over to back mode of ventilation and avoid consumption of oxygen as drive gas in a crisis situation. So this is one application. And liquid oxygen, I think the whole world came to know about liquid oxygen during our COVID pandemic, and even many countries, they had oxygen scarcity, and liquid oxygen was getting transported from wherever they had in excess to the areas of scarcity. Even otherwise, big hospitals used to have liquid oxygen plants. Now, liquid oxygen is a storage form of oxygen, and how much oxygen is available from liquid oxygen. That is very important to know. Liquid oxygen produces 861 liters of gas at about standard temperature and pressure for every liter of refrigerated liquid oxygen, which is boiled and heated up to that temperature. Okay, so 861 is the figure you need to remember. Three gas laws when we discuss about ideal gas equation. One is Boyle's law, which says at constant temperature, pressure inversely related to volume. Charles' law, at constant pressure, volume is directly proportional to temperature. Remember, this temperature will be in Kelvin. And the third gas law, Gay-Lussac's law, says that pressure varies directly, proportionately with temperature in Kelvin when volume is kept constant. So in nutshell, we can say that P1 V1 by T1 equals P2 V2 by T2. How to memorize these gas laws, which is constant in which law? So these are common mnemonic given in our standard teaching. Water boils at constant temperature. That means in Boyle's law, temperature is kept constant. And our dear friend Charles is under constant pressure. Okay, so Charles' law says keep the pressure factor constant and the other two varies proportionately. PV is equal to nRT. So R is the ideal gas constant. R is equal to 8.314 joules per Kelvin mole or 0.820 liter atmosphere per Kelvin mole. Okay. Dalton's law of partial pressures says for a mixture of non-reacting gases, the sum of the partial pressures of each gas is equal to the total pressure exerted by the mixture at constant temperature and volume. That means the P total is equal to the sum of the partial pressures, P1 plus P2 plus whatever plus up to Pn. The commonest easiest example is to see the total pressure exerted by our atmospheric air, which contains 21% oxygen, 78% nitrogen, and the other components. And the total pressure is actually the sum of the partial pressures exerted by the components of air. Henry's law is very important for us. It says for a constant temperature, the amount of dissolved gas in a liquid is directly proportional to the partial pressure of that gas, which is in contact with its surface. So the partial pressure P is equal to K into M, where P is the partial pressure of the gas, K is the Henry's constant of proportionality, and M is the molar concentration of the gas. About Graham's law states that the rate of diffusion or effusion of a gas is inversely proportional to the square root of the mass of its particles. We'll come to that when we discuss the applications of it. So having described gas laws very briefly and very briskly, let's time to start with the practical applications. The question is how Boden's pressure gauge will indicate the content of the oxygen cylinder. Okay, you know the Boden's tube pressure gauge is part of our cylinder pressure gauge and our pipeline pressure gauge. How it works, everybody knows. So the question is whether the pressure will give you the content inside the cylinder. The ideal gas law says pressure into volume is equal to N, the number of moles, into R, the constant, and T, the temperature. That means if you know the pressure, you indirectly know the number of moles inside the cylinder. So hence the pressure gauge actually acts as a content gauge as well. But does it apply to nitrous oxide pressure gauge? That's an interesting discussion, and I would like to get your viewpoint onto it.
Now it's time for you to find answers. You may pause the video, note down your answers. And Dr. Sanish will explain the answers at the end of this video itself. There you go.
Okay, just note down whether the following statements are true or false. Okay, nitrous oxide exists as a liquid at room temperature. Statement B, nitrous oxide Bourdon pressure gauge always shows 750 psig till all the liquid nitrous oxide becomes vapor. C, when all the liquid nitrous oxide converts into vapor state, the Bourdon's pressure gauge will act as a content gauge. And statement D, all are correct. Continuing with audience questions, what is pseudocritical temperature, and give an application in anesthesia. So nitrous oxide has a critical temperature of 36.5. That means it cannot be compressed into a liquid above 36.5 degrees Celsius, whatever be the pressure applied. But our room temperature of 20 degrees Celsius, it remains as liquid inside the cylinder in equilibrium with the nitrous oxide vapor above the liquid level. So how do you estimate the contents of nitrous oxide cylinder? A full E-type nitrous oxide cylinder will give you 1680 liters of gas at standard temperature and pressure. Remember, standard temperature and pressure means 273 Kelvin and 760 millimeters of mercury, that is 0 degrees Celsius. Now, how do you find the volume available at room temperature, 20 degrees Celsius? So now you have to convert the available volume from STP to a room temperature, that is 20 degrees Celsius. Here we take the help of our dear friend Charles' law. Okay, Charles' law is applicable. Remember, the temperature should be in Kelvin, not in degrees Celsius. So Charles' law says that V1 by T1 is equal to V2 by T2. So we know the V1, the volume available at 0 degrees Celsius or 273 Kelvin. And we want to know the volume available V2 at 20 degrees Celsius, that is 293 Kelvin. So solving it, we end up getting 1803 liters. Okay. Next application is to find out the amount of volatile liquid of a liquid anesthetic agent like a sevoflurane needed to make a non-percentage of vapors, or rather how much liquid agent, volatile agent is getting consumed if you keep a given percentage of dial setting for a given fresh gas flow. Again, we take the help of gas laws. Take an example of sevoflurane. We know that the molecular weight of sevoflurane is 200. The density of sevoflurane is 1.5. So 200 grams of sevoflurane, that is 1 gram molecular weight of sevoflurane, will get converted to 22,400 mLs of vapor. Correct? This is coming from our Avogadro's law. So 1 gram of sevoflurane will give 22,400 divided by 200. That means 112 ml of vapors. So far clear? Now we know that the density is 1.5. That means 1.5 gram is equal to 1 ml. Fluorine liquid equals 112 into 1.5. That means 168 ml of sevoflurane vapor. Clear? If you want clarification, kindly rewind and go through the slide once again. This is based on Avogadro's hypothesis. Again, this is for STP. You need to convert it into 20 degrees Celsius or room temperature. Again, you take the help of Charles' law. A shortcut for this is you can imagine 1 gram mole of vapor or a gas will occupy 24 liters at 20°C. Doing all the mathematical calculations, we'll come to know that 1 ml of liquid sevoflurane will get converted to 180 mLs of sevoflurane vapor at 20°C. Next practical application is why is it said that oxygen cylinder should not be kept under the sun? Oxygen cylinder safety demands that it should be kept in a cool, dry place. So if oxygen cylinder is kept under the sun, the temperature increases, and according to Gay-Lussac's law, pressure is directly proportional to the temperature when volume is being constant. So pressure builds up inside the cylinder so much that the cylinder might even explode. So there are instances reported in the literature. So oxygen cylinder should be stored in cooler place, and there are some safety mechanisms or safety valves incorporated in the cylinder valves, be it fusible plug with Wood's metal, frangible disc or rupture disc, or safety relief valves in the oxygen cylinder yoke. Next, discuss why should you open the cylinder slowly. Okay. Cylinder should be opened slowly, as rapid opening of the valve will produce a rapid flow of oxygen into the space in the tubing of the yoke assembly and the pressure regulator, producing an adiabatic process, as rapid compression of oxygen in the narrow tube can produce a high temperature leading to possible explosion. Hence, the oxygen cylinder should be opened slowly to prevent this adiabatic process and risk of explosion. Now we switch over to the next phenomenon called Venturi effect. You know that Bernoulli principle says that the total mechanical energy of moving fluid, comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of fluid motion, the sum remains constant. Again, it's time for audience question.
Now it's time for you to find answers. You may pause the video, note down your answers. And Dr. Sanish will explain the answers at the end of this video itself. There you go.
Well, the question is, can you identify the equipment? So we'll come to the answer key later. These are the applications of Venturi principle. When we use Venturi oxygen mask, when we use nebulizer, Sanders jet ventilator, we use suction apparatus producing vacuum with the help of high flow oxygen, modern vaporizers like direct injection of vapor anesthetic, and for making drive gas for bellow-in bottle ventilators, we use Venturi principle in anesthesia. In Dragon machines, second stage pressure regulators are not there, as the gases from the pressure regulator at pressure of say 45 to 60 psig move towards the flow meter assembly. They have to flow through a flow resistor, which are nothing but sudden narrowing of the tubes. So according to Bernoulli's principle, here the pressure is further reduced, but the flow is increased before reaching the flow meter assembly. When we do Pethix test, again we are using this Venturi principle. In this test, after closing the expiratory valve and the inner tube, keeping 3 liters of flow of oxygen, one should see that the reservoir bag is full. Then simultaneously oxygen flush is activated, and also the thumb occluding the outer tubing is released. If the inner tube does not have any leak, then the reservoir bag will be seen to collapse. This is due to Venturi effect, because at the opening of the inner tube into the outer tube, due to the flow of 30 to 70 liters of oxygen, which produces a sudden fall in pressure, causes the reservoir to collapse. If there is any leak in the inner tube, the reservoir bag may not collapse. So that is Pethix test for you. Moving ahead to Reynolds number. We are all familiar with the Reynolds number, which actually deals with factors that determine the turbulent flow commencing, which can be combined into an equation called Reynolds number equation, where we have the players like velocity, density, the diameter of the tube or orifice, and eta, the viscosity. So in nutshell, what you need to remember is when the Reynolds number is up to 2000, the flow will be laminar, and when it is above 4000, it will be a turbulent flow. Between 2000 to 4000, it will be a mixture of laminar and turbulent flow. When we discuss about flow meter assembly, we need to understand the difference between tube and orifice. So how does the tube look like? Tube means the diameter is small and the length of that given pathway is much larger. And when it comes to an orifice, you can see the diameter is much larger than the length of this opening. So that is orifice. Now you look at the rotameter top tube, where you can see at low flows, length is much more than the diameter of the gap between the tube wall and the bobbin. So it becomes tube effect at low flows. When it comes to higher flows, you can see the diameter is much more than the length of the constriction. So it becomes an orifice effect. Surely it will be reflected in the effects, gas flow effects also. So at low flows, gas flow is laminar, and hence viscosity of the gas is important. Hence Hagen-Poiseuille law applies here. Here you can see the flow is equal to pi p r raised to 4 by 8 eta L. In nutshell, you can remember it as the flow is directly proportional to the pressure drop P. Okay, so as the flow rate increases, the density of gas affects its flow, because now the flow has become an orifice effect. Okay, and the flow has become turbulent. Now the pressure drop increases as the square of the volumetric flow rate. That means doubling the flow rate quadruples the pressure drop. So effect at high flows, and we can derive that now the flow is proportional to the square root of pressure with turbulent flow. That means in high flows. Remember, in low flows, it was laminar flow, and the flow was directly proportional to the pressure. And in high flows, flow is directly proportional to the square root of pressure. So what is the implication? The graduations on the flow meters are not uniform. Okay. You also have to remember that the reference temperature and pressure conditions for gas flow meter calibrations are 293 Kelvin and 101.3 kilopascal. That means around 20 degrees Celsius and 1 atmospheric pressure. What happens at high altitudes? The flow meters calibrated at sea level can deliver higher flows than indicated due to a reduced density of gases. The error can be up to 20% at an altitude of 3000 meters from the sea level. A hazard may arise when low flow oxygen is mixed with the high flow of nitrous oxide. Even in oxygen cascade, you can understand the difference in the partial pressures at different steps in the cascade. You can appreciate the cascade drawing or the tracing at sea level versus that tracing at high level. Now the issue is what adjustment you need to take for your vaporizer settings if you are anesthetizing a patient at altitude. The user's manual of some of the vaporizers limit the use of halothane and isoflurane to altitudes of more than 1450 to 3000 meters above the sea level. Since the boiling point lowers at high altitude, the temperature compensation system will not be enough to control the gas evaporation. Most vaporizers are built to work under temperatures of 10 to 40 degrees Celsius, though it varies according to the manufacturer. Now we take an example of high altitude and variable bypass vaporizers. The output of a variable bypass vaporizer is typically calibrated to atmospheric pressure. At high altitude, that means at low atmospheric pressure, the output no longer corresponds to the dialed percentage. Again, you can remember that the saturated vapor pressure as a physical property in the vaporizing chamber remains unaffected by the ambient pressure. We'll take an example. If ascending from sea level to 5,500 meter air pressure, getting half atmospheric pressure. So now the atmospheric pressure is 380 millimeters of mercury, half what is there in the sea level. And the setting that would previously deliver 2% isoflurane will now deliver 4%. That means the output volume percentage is doubled. Okay. Importantly, because 2% of 760 millimeters, that is 15.2 millimeters of mercury, is the same as 4% of 380 millimeters of mercury, which is again 15.2 millimeters of mercury. The partial pressure delivered would remain the same. I hope it is clear. Though the volume percentage output is doubled, since the atmospheric pressure is halved, the ultimate partial pressure delivered will remain the same with regard to variable bypass vaporizers. And remember that the depth of anesthesia is dependent on the alveolar partial pressure rather than the vapor concentration. Not the point, dependent on alveolar partial pressure and not the vapor concentration. So although the concentration delivered is double, the clinical effect remains the same. Titrating anesthetic depth to concentration by using minimum alveolar concentration MAC parameter may not be very accurate. The use of MAC instead of partial pressure, that is MAPP, minimum alveolar partial pressure, may lead to significant underdosing of the anesthetic agent and therefore increases the risk of anesthesia awareness at altitude. So at high altitude, remember to use partial pressures, minimum alveolar partial pressure instead of MAC, which is defined for 1 atmospheric pressure. We'll take the example of desflurane vaporizer, which is a different category of vaporizing equipment. In contrast to variable bypass vaporizers, the output concentration of desflurane from Tech 6 vaporizer is constant across the range of barometric pressures. Is it a boon or a bane? Remember, Tech 6 vaporizer is a gas blender type of vaporizer. Therefore, at high altitudes, the partial pressure of desflurane will be lower at a given Tech 6 vaporizer setting and output, that is volume percentage concentration, than at sea level, leading to underdosing of anesthetic unless an adjustment is made according for the high altitude. How do we do that? Required vaporizer setting in Tech 6 vaporizer equals desired vaporizer setting at sea level into 760 millimeters of mercury divided by local barometric pressure in millimeters of mercury. So this will give you the revised vaporizer setting if you are using Tech 6 vaporizer at high altitude. Few points on oxygen at high altitude. Remember, a high concentration of oxygen should be given at least 40% higher than at sea level during perioperative period at high altitude. Anesthesia deprives compensatory hyperventilation at high altitude. Irreversible hypoxic brain damage may occur in case of apnea or airway obstruction due to a lower PaO2. Patients at high altitude are unlikely to compensate for metabolic acidosis following hypertension or hemorrhage as a buffering capacity is reduced, and in high altitude due to low alveolar and arterial oxygen tension, a high concentration of oxygen should always be given. Take an example of a pneumothorax patient airlifted to a different setting. If you look at the Boyle's law, P1 V1 is equal to P2 V2, we can calculate the change in volume at different altitudes. Say, for example, a patient with a simple pneumothorax being shifted to a local hospital by airlifting. They have a pneumothorax volume of, say, 1500 ml at sea level. At an altitude of 1 kilometer, assuming the patient remains at constant temperature, we can rearrange the formula to find out the V2, how much will be the volume of the pneumothorax. We'll find that at high altitude, it actually increases. The pneumothorax increases at the volume increases at lower atmospheric pressures at constant temperature. So before concluding, let me give you the answers of some audience questions which I posed during this lecture. Okay, these are the answer keys. True or false? That was regarding our nitrous oxide cylinder and the content gauge by the Bowden's pressure gauge. Nitrous oxide exists as a liquid at room temperature. True, because its critical temperature is 36.5. Below critical temperature, it is possible to liquefy at a higher pressure. So at 750 psig inside the cylinder, nitrous oxide does exist as liquid at room temperature, that is 20 degrees Celsius. Nitrous oxide Bowden pressure gauge always shows 750 psig till all the liquid nitrous oxide becomes vapor. Yes, the vapor in equilibrium with the liquid form of nitrous oxide continues to have a pressure of 750 psig. So even when the nitrous oxide cylinder is half exhausted, the dial in the Bowden's pressure gauge will not change. So if you want to know the content of liquid nitrous oxide, how much is remaining, what you need to know is the how much weight of the nitrous oxide is remaining. For that, you need to know the tare weight of the cylinder and the total weight of the cylinder, from which you will get the weight of liquid nitrous oxide. So if you know the weight has become half, you can say the content has become half. Weight has become 1/4. The cylinder is only 1/4. And when the dial starts falling from 750 psig, you can understand that no liquid is remaining inside the nitrous oxide cylinder and it's almost empty. Okay. So when all the liquid nitrous oxide converts into vapor state, Bowden's pressure gauge will act as content gauge. That's a true statement. So here is a discussion on a comparison between what is the gas, what is vapor. So vapor exists as gas in gas phase in equilibrium with identical liquid or solid matter below its boiling point. That is very important. Say for example, oxygen and nitrous oxide. Oxygen critical temperature is minus 118 degrees Celsius. Okay, so how much ever pressure you apply at room temperature, it cannot be liquefied, so it exists only as a compressible gas. Nitrous oxide, the critical. Next question was about pseudocritical temperature. It's an interesting concept. Pseudocritical temperature is the temperature at which a gas mixture separates into its components. It applies to mixtures of gases. Or example from anesthesia is Entonox, that is 50% mixture of nitrous oxide in oxygen. Remember, critical temperature of a substance is the highest temperature at which it can exist as a liquid. At temperatures above the critical temperature, the substance cannot be liquefied regardless of the amount of pressure applied. So here you can look at the diagram and say, check the isotherms of nitrous oxide. So beyond its critical temperature, 36.5 degree, it exists only as gas, how much ever pressure you are going to apply. But below 36.5 degrees Celsius, it's a different entity. It can exist as liquid, liquid plus vapor, or even as a vapor. So that's what happens inside the nitrous oxide cylinder. So in this regard, I would like to request our residents and postgraduates in anesthesia to check the definitions of what is critical point, what is triple point, etc., because these points might come up in your viva. So I've already explained critical temperature of nitrous oxide is 36.5 degrees Celsius. At 20 degrees Celsius, at a pressure of 51 atmospheres, that is 750 psig, it exists as a liquefied nitrous oxide inside the cylinder. Oxygen critical temperature is minus 118.6 degrees Celsius. So oxygen cannot be liquefied at room temperature and it exists as a gas, no doubt. Coming back to Entanox. Entanox has a pseudo-critical temperature of minus 6 degrees Celsius. Once the mixture is happening, now you have a new critical temperature for that mixture, that is the pseudo-critical temperature. So now you can understand that above minus 6 degrees Celsius at a cylinder pressure of 137 bar, it exists as a compressed gas for storage at room temperature. Okay. The pseudo-critical temperature is minus 6. So at room temperature, it cannot be liquefied. It doesn't exist as a liquefied form. It exists as compressed gas. So in room temperature, a mixture of 50% mixture of nitrous oxide and 50% of oxygen, that is N10OX, exists as compressed gas. Remember, it must not be stored below its pseudocritical temperature or it will separate under a process called lamination, which can have catastrophic effects. Next audience question, identify the equipment. Hope you got, everybody got it correct. Sanders manual jet ventilator set. Okay, with that, I think it's time to wind up this session. I hope you enjoyed listening to the clinical applications or practical applications of what we learned in the lecture classes as gas laws and anesthesia. You can feel free to send me feedback on my email. You can also visit my website, www.onlineanesthesiatools.com. It's always been a pleasure to bring videos for you from Anesthesia Tools. It's me, Dr. Sanish, signing off. Goodbye.